we now discuss piezoelectric actuators, and for those of you who are interested in more details, especially about applications, I suggest the book by Kenji Uchino, Piezoelectric Actuators and Motors. Piezoelectric motors are just a special kind of piezoelectric actuators, and we will cover them in the second part, and you will find a lot of discussions in Kenji's book about that. So I warmly recommend you to check this book if you're interested about principles and many different types of piezoelectric actuators and motors and applications. So for piezoelectric actuators, we use converse piezoelectric effect, usually driving them with voltage and getting displacement or force out. As I will mention immediately, if you take this relationship here and then look for a D33 for a longitudinal coefficient, you find out that just as for direct effect, there is no dependence of displacement on dimensions, whether you take a very long or very short for a given voltage, not electric field. For a given voltage, displacement is independent on the size of the actuator. This is not the case for transverse D31 effect, where displacement is dependent on dimensions of the sample. If you consider voltage and not electric field as the driving field. So in this figure here, the thickness here is L3 and L1 is the length. So if you take very long actuators and you look in D31 effect, you will have a large effect. So if there is no force applied, if it is a free actuator, you would in fact get displacement proportional to directly proportional to the voltage. That is a displacement actuator, and that would be used to move objects which are not fixed, light objects, light in optics, and so on. If you clamp your actuator completely, then it will exert a force on the object, and then it will exert then it will act as a force generator, and the formula of that force under ideally clamped conditions is given here. So any actuator can actually be considered both as a displacement and force generator, as objects are always the object that you are going to move will always be partially clamped, or your actuator will be partially clamped. So I suggest to you to look at this second formula and try to derive it, and you simply have to use, while here you are using just, while here you are just using the a piezoelectric part of the constitutive equation. Here you would have to also use the mechanical part, because you cannot ignore that clamping force, and from that you can derive this formula. Try to do that. What is the size of the converse piezoelectric effect? Well, you remember when we were discussing direct effect, we said that piezoelectric coefficient in practical piezoelectric materials goes considering order of magnitude from 1 to 1000 picocoulombs per Newton. And for converse effect, well, the number is the same. We just express it in picometers per volt. So you would have something like 2 picometers per volt in quartz, up to 2000 picometers per volts in relaxor ferroelectric crystals. So we can look at strain and the displacement. So if we look this first equation here, where I'm considering a field of 10 kilovolts per centimeter, that's 1 kilovolt per millimeter, piezoelectric coefficient of 100 picometers per volt. So typical PZT, hard PZT, you would get a strain of about 0.01%. If we, on the other hand, consider just this relationship here, and we apply 100 volts, then displacement for the same 100 picometers per volt would be something like 10 nanometers. This is not much, but you don't have that many actuators that can give you such small displacements with a good precision. We can resort to different ways in amplification of displacement of actuators. So one of them is to use multilayer actuators. So how does this work? Where for a single actuator, you get that displacement is equal to product of piezoelectric constant and voltage. And if we have n elements, then that would be n times that. How do you make this? Well, there are several ways in which this can be done. You can first, how connections are made. Usually you make connections this way. You would put piezoelectric elements that are poled like this and then stack them. And this can be done either by tape casted layers or by just piezoelectric stacks of individual piezoelectric discs. And then you would have the electrodes that connect this side of samples and other electrodes that connect this side of samples. So this just marks electrodes, and these would go would be connected here, also here the same. So this would be connected there, and this would be connected here. So it's mechanically in a series and electrically in parallel. If you have piezoelectric stacks, you would just put discs as it is shown here. So the black would be electrodes, and white rectangles are piezoelectric discs. They usually have a shape of a ring like this, and then you would put a bolt through that hole and tighten it to keep the actuator under compression. And so you would work under extension. You would apply field only in one direction. Application of the field in one direction is necessary first not to depolarize the field. You can go in a negative against polarization, but not too much. Usually it's about 10% or so against the polarization. While in the direction of polarization, you can usually apply large forces, and the compression is needed because is among other things needed because piezoelectric materials, ceramic materials that are mostly used for piezoelectric actuators can be easily broken on tension. but on compression they are much more difficult to break, and that is because under compression you close the cracks and they cannot propagate that easily. So when you take a piezoelectric actuator, you usually see this envelope which is made of steel or some other materials as such. The fact that you have a multi-layer means that you either can get for a given voltage n times larger strain, or what is important, you can get a given strain with a n time smaller voltage. So you can actually achieve large displacement with small voltages. You can generate huge forces, tens or hundreds or even thousands of kilograms with piezoelectric actuators. You can lift very heavy objects, and unless there is depolling, because you are applying some pressure on them, they can be very effective force generators. If you don't use stack of discs, piezoelectric actuators can be, that stack of discs is, on one hand, it's easy to make because electroding is simpler and there are no other problems that I'm going to explain with tape casted actuators, but you have to pile them up, and the tape casted actuators are in that sense easier. They use the same technology that is used for multi-layer capacitors, and this is very well understood. So what you would do is you use a tape, ceramic tape. How can you make a tape of ceramic? Where you mix it with the polymer, you dry it, you have a ceramic tape which is very thin, then you put electrode on the top of that, then you take next tape, and then you put electrode on that one, and then you pile. You can pile hundreds of these tapes on the top of each other. You get very thin layers, so you need very small voltages. And then after you screen print all these electrodes, you press everything, put it in a furnace, you remove the polymer, and you get just ceramics and electrodes which are fused, sintered together. The problem here is that at the end, the electrodes would cover only part of the ceramic. So these are electrodes. Have electrodes like this and like this. And then you connect here voltage. So only this part of the ceramic would be under the field and would extend, or whatever it does under the field, while these other parts will be subjected to a lot of stresses, and that is where actuators may easily fail, break. So those are weak points, the parts that don't follow the field. So here you will have a large strain, and not here, and that difference in strain, that strain gradient would break them. Also, you would have some transverse effects. Here you are using D33, but you would also have some D31 effects, which would also apply a force on the interface between ceramics and electrodes. And also, since you have to fire everything at a high temperature, the electrodes may diffuse into ceramic. If you use, for example, silver electrodes, it's very mobile and will diffuse in a ceramic and make it electrically weaker, you can have degradation and other properties. Now I'm describing problems. However, these actuators are still the leading actuators. They work very well, and they can work for years and years and make billions of cycles. However, the end user should be aware what can happen. So one of the things is don't apply negative field against the polarization, and you usually from the producers buy driving the power supply to drive them, to electrically drive them, which doesn't allow you to allow pressure, to allow voltage, which would depolarize. Here are pictures of some of the piezoelectric actuators from Physica Instrumenta, one of the largest producers in Europe. You see the metal, the steel parts, and the ceramics are inside. Here you can see some of the ceramics, how it looks like. You can see many considerations that you have to take into account when using piezoelectric actuators here. And I will not go into too many details here. There is no one rule how to keep actuator, how to predict a lifetime of the actuator, because this depends on the temperature at which you use it, whether you are applying always the maximum field that you can apply or lower fields. It depends on the frequency at which you use it and so on. There you have to be careful if you are using very thin elements, tape casted actuators, then the capacitance is going to be very large. And if you have 100 of these layers, then the capacitance of the whole actuator can be really indeed very large, and that can make it difficult to drive it, to supply that much current to you apply voltage, but your power supply also have to apply the current, because by applying electrical field, actuator also acts as a capacitance, and you have to charge that capacitance, so you have to provide high current. If you're interested, you can read this to see what different considerations you can get, but they are excellent in general, providing you many hundreds of millions of cycles. And what is very important with respect to other types of motors, such as electromagnetic motors, is that there is no wear and tear, because there are no moving parts in these motors. It's just extension there is in these actuators. So what are some of advantages of piezoelectric actuators? Well, you had sub-nanometer resolution, which is very difficult to get with, let's say, hydraulic or electromagnetic step motors and other types. You can have a generation of very large forces. You have a very quick sub-millisecond response. There is no backlash. There are no magnetic fields. This is very important that there are no magnetic fields, because sometimes in sensitive electronics, you cannot afford strong magnetic fields that you would have in electromagnetic actuators. So piezoelectric actuators have been used here at EPFL to make motors to drive disks in computers, the hard disks in computers, while you had these rotational ones. Now we are using solid state memory devices, so this is no longer important, but there are still many applications in which you want to avoid magnetic fields. They have extremely low steady state power, because they are not, they are perfectly ideally perfectly insulating. There is very leakage, very little current involved in them. For example, you apply DC voltage, you polarize it, you keep it there, and there will be very little current there. So the power is in general lower than certainly always under any operating condition than electromagnetic actuators. There is no wear and tear because there are no moving parts. Also very important consideration is that they are vacuum and clean room compatible. Many hydraulic and other types of actuators would contaminate vacuum and clean rooms where you require very high purity because they let particles have liquids and so on. And finally, they can be operated at cryogenic temperatures where those that have moving parts or hydraulic ones would not operate. One special type of actuator are biomorphs. So these are exactly the same constructions as what we were discussing with biomorphs used for direct piezoelectric effect as sensors, except that here you apply voltage and you get bending. You are using actually D31 mode, even though you are applying voltage like this. The extension in that direction is very small. What you are using is transverse extension, and then for reasons that we discussed with the sensors, the material will bend, and that bending is what you are using for actuation. This is the principle on which work this cooling device by General Electric that I told you in the introduction. So you would basically have two metal pieces on which you glue piezoelectric discs. And then when you apply a voltage on these piezoelectric discs, because they will change their size and metal tends to oppose it, the whole structure will bend either like this or like this, and that will cause air to be either expelled or if you want, inhaled inside the structure, and with that you can cool. And big advantage over normal ventilators that you're using in your computers is that these don't make, there is no ventilator rotating, there is no rotating part, and therefore they are much quieter. The only noise is air moving in and out. So you can easily get displacements of 1 micron or even more with relatively low voltages. You can, they of course produce very little force, so they act on gases and such, light used in optics. You can increase force that they can generate or support if you or mass that they can lift if you make spherical shape. So this is a side, this is a sphere that has two piezoelectric elements glued to each other, so it's a biomorph. It's just that it is cut in a form of a disc, and this is a side view of the same disc. And then when you apply a voltage, this will form a couple, and you know from architecture that couples can stand very high forces. So with such a disc, which is just a few centimeters large, we were able at several hertz to lift 2-3 kilograms very easily and to sustain that motion for a while. So these are called disc benders. They are very thin, and when they vibrate, they can, for example, control the flow of air and can be used as anti-noise generators. We had a project with European aerospace industry, in which attempts were being made to use different types of actuators to reduce noise in avio engines during landing and takeoff. And one of the actuators that showed promise were these piezoelectric actuators. In general, you can say that if you get a very large displacement, the forces will be low, generated forces will be low, and vice versa. The bigger is the force that you can generate, the smaller is the displacement. You can use amplifications, but always at this cost. The bigger is the displacement, that mechanical structure you have to build around your actuator to increase the displacement will usually decrease the force. It's interesting to see how people build different types of actuators. Here is the actuator that was made by Bob Newnham and his team at Penn State University at the end of the 80s, which is still used. So the blue is piezoelectric material, and orange, red is metal, brass, for example, copper, and you apply electric field, and this material will expand in a longitudinal direction, which is less important here. Much more important is a transverse movement, and that transverse movement of a piezoelectric material under field will apply forces which will deform these metal caps, and they will give you very large displacement. To increase that displacement, you can make this multilayer, or you can stack several of these munis or symbols on the top of each other. So here you have a PZT, pure, and then different types of these munis, and you see that you can increase by maybe 2 orders of magnitude response of these munis. These actuators were used to put on the skin, and then when they act, they open pores in the skin through which you can inject insulin into body. So you don't have to inject with syringe insulin, and this is very good. I think Medtronic used that for insulin pumps. The problem with that is that if you have a direct contact with the skin, then you can also open the pores for bacteria and other stuff, and that can obviously that can be a problem. When I'm mentioning these pumps, it's interesting to look at fatigue and failure of actuators. And here is an example of an insulin pump, which we tested. So you have a thin piezoelectric disc, this black part here. You put it on a thin substrate, such as glass, quartz glass, and then you have a silicon substrate, which I cannot show you exactly how it looks like, but it is micro machined in such a way that by applying force or applying voltage on this piezoelectric disc, you will be opening some valves and closing others, and that would cause liquid to be pumped in and pumped out of this structure and deliver insulin in a nanoliter, so during the day. What you observe is that the maximum displacement drops down with the time. If you stop using it, then you continue next day, you see that there is a little bit of recovery, and then the dropping continues, but at a lower rate. And troubleshooting of this thing is very difficult. And what you usually find in this type of devices, it is not the material or your structure that fails, but interface between them, how you glue that piezoelectric disc to your structure. That's usually a weak point. Interfaces very often are weak points in material science. So what kind of glue you choose. Hysteresis and creep in ceramic actuators we have already discussed, and I will not spend more time on that. We will discuss a little bit this actuator, which doesn't show any hysteresis but has a very strong nonlinear response, but we will do it in the second part of this lecture on actuators and motors.